In this tutorial, I will explain theorems for free and parametricity results from the point of view of a practical functional programming. In this tutorial, the code examples will be in Scala, but the same results apply to any functional language. What is parametricity and what are theorems for free? Before I talk about the theory, I will motivate from the point of view of a practical programmer, what are these results that we might care about? And from the point of view of a practical programmer, parametricity is a theory about certain refactoring of code, a theory that explains why specific kinds of refactorings always work correctly. So I will first talk about those refactorings from a purely practical perspective. Consider one example where we work with some database. Let's say we have a function like this that gives us some kind of iterator or stream of rows of a database, and we want to extract certain information from that database, for instance, user information, some kind of data structure, which is extracted from the row using this function. So there are two ways of doing this. First, we can convert the database iteration into a list, and then we can extract the user information from each element of the list. Or we can first extract the user information directly at the level of the iterator, and then we can convert the results to a list. Now these two code snippets would give the same result. A second example is when we want to exclude some rows from the database, for example, because the information is in some sense invalid. So then again, we have two ways of doing this. First, we could extract the user information, and then we can filter valid users. Or we can first filter, but then the filter must be done like this. We must modify the filtering predicate so that it is a composition of getting the user information and then applying the validity condition, because in this case the row will be of some other type. So first we need to extract user information from the row, and then we can, after filtering, again map the resulting stream to get the user information. Now, as before, these two code snippets give exactly the same results. Now, which one of them is to be used is up to the programmer. It could be sometimes better to use one or the other. For instance, first it could be good to filter the ones that are not necessary to be processed and then process them. But maybe this function becomes very difficult. If that is so, then better to do that, and so on. But in any case, the programmer is free to write one or the other code snippet, and it is guaranteed that the results are the same. So this refactoring is guaranteed to be valid, correct. This refactoring is guaranteed to be correct. Why is that? Why are they guaranteed? This is not an accident, and they're guaranteed to be correct because actually the functions toList and the functions filter have special properties which are called naturality, or these functions are also called natural transformations. So the toList function can be seen as a function of this type signature from some kind of stream of type A to a list of type A, and here type A is arbitrary, so it's a function that's parametrized by the type. And natural transformations are functions that are parametrized by the type, like this. They have the type signature from one type constructor to another type constructor, like this, and they must be implemented by code that works in the same way for all types. So that is a programmer's definition of a natural transformation. The filter function does not have a type signature that looks like this, but after some massaging you can make it look like this, and so it's really also a natural transformation in disguise. From the point of view of formal rigorous reasoning, we need to formulate equations or laws that show that natural transformations work correctly. And so those are called the naturality laws. In order to write those laws, first let us abstract a little and say we are using toList as a function of this type signature, and we're using an arbitrary function f. So here this function was getUserInfo, but the same will be true for any function f of any type a to b. And then the refactoring is that we first apply toList and then map with f, or we first map with f and then apply toList. So the law is that these are equal. So for any function f, this code gives always the same result as this code. Now these are functions that need to be applied to some value of type stream of A. So for any value of type stream of A and any function f, this left code snippet must be equal to this right code snippet. The refactoring involving filter is written in a similar way as a law or equation, where let's say we have a type signature like this. And then for any function f and for any predicate with this type signature, we have this equality. So this function will give the same results as this function. So this is a naturality law for filter, and this is a naturality law for toList. So in this way we reformulate our expectations about these functions in terms of laws. So the general formulation of a naturality law for an arbitrary natural transformation T looks like this. A natural transformation T must have a type signature of this kind, where f and g are some type constructors that are covariant, both covariant. And applying this transformation T before applying map f equals to applying this transformation T after applying map f. Now there are some details here that need to be spelled out. So we are using a function f of type a to b. So when we apply T, it means we start with some value of type f of a. We apply first T with type parameter a, because that's what we need to do. The result of g is g of a, and then we apply the map function, or map method, for the type constructor g, or we assume that it has the map method. In other words, we assume that the type constructor g is covariant, or in other words, is a functor. And the result will be a value of type g of b. Or we could first do a map, which will be a map for the functor f. Here it was for the functor g, here's the functor f. So it's important, it's a different function here. The map, the name is the same, it's a map here and the map here, but these are really different functions. The code of these maps is different. So first we apply this map of f, we get f of b, and then we apply the transformation T with type parameter b. So then we get g of b again. In this way we write this diagram, which is called the type diagram, indicating the types of initial values, intermediate results, and final values. And this diagram gives us two different routes through the graph, and then it means the results must be the same. So the results of going in this way must be the same as the result of going this way. And that's exactly the same as writing this equation. T and then map f equals map f and then T. Except that, of course, the T here is with type parameter A, T here is with type parameter B, and these maps are different, as I just said. So this is the naturality law in the general formulation for an arbitrary transformation T. So if transformation T has this type signature and satisfies this law, it's called a natural transformation. So that is the mathematical, rigorous way of requiring naturality, or saying what it means to be a natural transformation. But this law is basically showing our intuition for how code should work, what kind of refactoring should be possible for code. We expect that this code, if it works the same way for all types, would satisfy this law. Because how can it work the same way for all types A? Well, f of A is some kind of collection or container with values of type A, and G is another container or collection with values of type A. But we are not allowed to know what the type A is. So we can only take some values and rearrange them in some different order maybe, or we can ignore some values from here, or we can duplicate some values from here, but we cannot make any new values. And we have to do this rearrangement in the same way for every type A. So for whatever the type A is, we do this rearrangement in the same way. So we just rearrange this data. And if we do that, then it doesn't matter if we first apply map F and then rearrange, or we first rearrange and then we apply map F, because this rearrangement doesn't know what type we're rearranging. So we could rearrange the transformed data, or we can rearrange the initial data, and that rearrangement has to be the same. When we say this rearrangement has to be the same, it means the code works the same way for all types A. And so we have shown that this expectation of a programmer, the code should work the same way for all types, is exactly represented by this law of naturality, that the order of applying T and map F can be permuted, and the result should stay the same. Here are some more examples of this law for specific functions. The head option is a standard method defined for a list returning an option. It can be seen as this function, so that is a typical type signature of a natural transformation. And the naturality law can be written like this: we first map and then head option, or we first head option and then map. Now this map is for an option on the right hand side, and this map is for the list on the left hand side. A programmer expects this to be true, certainly, since the head option just takes the first element of the list. Doesn't matter what type that is. And so that is the rearrangement of a data in a collection. So if you think of an option as also kind of a collection that could have 0 or 1 elements, and list is a collection that could have 0, 1, 2, and so on elements, and we're just rearranging existing data from this collection into data in this collection. We're not looking at any values or types specifically. Another example is reversing a list. It has this type signature, so that is a type signature of a natural transformation, and it satisfies the law of natural transformation. So if we can first map with F and then reverse, or we can first reverse and then map, the results are the same. It's a reversed list with transformed values. Another example is the method pure. It has this type signature. Now this may not look like it has the type signature of a natural transformation, but it is, because this could be seen as a type constructor. Let's call it identity functor, which is defined as just A. So id of A is just A, but it could be viewed formally as a type constructor nevertheless, and it's covariant, so it's a functor. And its map function is just identity. Because its map function is just identity, the naturality law doesn't show a map method on one side of the law. It does have it on left side of the law, but not on the right side of the law. It doesn't look like we had a map method anywhere, but actually we do. It's the identity that we don't see. And finally, the length function that takes the length of a list. It has this type signature, but it again may not look like it has the type signature of a natural transformation, because it should be type constructor of A going to type constructor of A, but this does not have the form of a type constructor of A. But it does if we pretend that this is just some kind of type constructor like this, which we can define, certainly constant functor, which always has just the type int. It ignores the type parameter A. And if we do that, the map function is just a function that ignores the function f. It's an identity function that ignores the function f. And then the naturality law looks like this. So we have a map of f on the left-hand side, but we have no map, no f on the right-hand side. But this is still a particular case of the naturality law, just because the map function for the constant functor is trivial, and it's ignoring f and always returning just the integer of the previous value. So then this is the law that says you can map a list, but its length remains the same. Well, this is certainly what a programmer expects. But it's interesting to see that these properties are special cases of naturality law, if you look at it in a certain way. Another use of naturality laws comes in type classes. Now, type classes, I'm not going to talk about what those are, so I expect you know what those are. Specifically type classes with type constructors. They usually have methods like that: map, filter, flat map, pure, and so on. And these methods usually need to satisfy many laws, such as these. I'm not going to write them out. I'm just going to mention that most of these functions must also satisfy naturality laws. So most of them must be natural transformations of some sort. And when you implement a type class for a specific instance, you must check the laws. Now, it's a lot of work to check those laws, and you have to check it every time that you implement a type class. Another thing that naturality laws are giving you is that you can simplify the type class if you know that naturality laws hold. So, for example, the flat map and flatten methods are equivalent. You can express one through the other if you assume that flat map satisfies a naturality law, and they're equivalent. And filter is equivalent to a function deflate with this type signature if you assume that filter satisfies naturality law. And pure is equivalent to just one value of this type if you assume that pure satisfies naturality law. So in this way you can simplify the formulation or implementation of a type class, because it's easier to implement functions with these type signatures. They're shorter and simpler type signatures that have fewer type parameters, given naturality laws. So this is another application of naturality laws that comes when you implement type classes. So now we are ready to talk about what the theorems for free and parametricity theory gives practical programmers. So the name theorems for free comes from this paper by Philip Wadler. Here's the link to that paper. The quote, from the type of a polymorphic function we can derive a theorem it satisfies. Every function of the same type satisfies the same theorem. Now, we can translate this into modern terminology saying that given a type signature of a function, you can derive an equation that the function satisfies. And this equation is the naturality law that we have seen before. But actually, Theorems for free, as I will show, gives laws that come in two flavors. There are two versions of the laws, and sometimes it's one and sometimes it's the other. I will explain when that is so. The first is naturality laws, and those are the ones I was talking about. There are these laws that say that we can change the order of applying map and some transformation. So that is a naturality law. And there is another called dinaturality, or dinaturality laws, which is much more rarely used. And that's a generalized form of naturality laws. So naturality laws are a special case of dinaturality laws. So parametricity theorem is a theorem that says that if a function t with this type signature is implemented using fully parametric code, then it satisfies a dinaturality law. I will explain in the next slides what those are. What is the fully parametric and what is that dinaturality law? Now, naturality law, I already explained what that is. And so dinaturality is just a little more general. Furthermore, the parametricity theorem gives you a recipe for writing that law. It's kind of an algorithm. You can automate that from a type signature. So you give a type signature of this kind with arbitrary type constructors, and you can write down that law. For each type parameter that t has, you have a different law. So one independent law per type parameter. Now, if t has more type parameters, so this, for example, p of abc into q of abc or something like that, then you have 3 different laws. So in most cases, as I said, this is going to be a naturality law, really. But in some cases, it's not. I'll show examples of that. So the usefulness of this theorem is that fully parametric code is a rule. It's almost always the case in functional programming that we write that kind of code. There are some exceptions, but if we write that kind of code, then it's not necessary to verify the laws. And so then we save a lot of time, we simplify our code, simplify type class definitions. We don't need to verify naturality laws. They hold by parametricity theorem. So that is the real value of this theorem. So that's why it's called theorems for free. So we don't have to verify these laws. However, this name for free is really a misnomer. It is not for free because you have to show that your code is fully parametric. I will talk about this now. So the practical consequences is that programmers need to do this. They need to recognize and write fully parametric code, which is code that works the same way for all types in some sense, but then there is a specific rigorous description of what that means. The programmer should be able to recognize and refactor code according to naturality laws, just the way I was showing. The programmer also should be able to implement the map method for any covariant functor or contravariant functor. For contravariant functors, it's a contramap method. But actually, if you want to be able to implement map for any covariant type constructor, you must be able to also implement contramap. There's no way out. So it's kind of the same thing. To be able to do one, you have to be able to do the other, and vice versa. You need to recognize that this refactoring is correct and recognize what simplifications you can have in your code. So the goal of this tutorial is to show you at least some of these things, how to write and recognize fully parametric code, and how to write the law. Implementing map for any covariant functor is not in this tutorial. But I have another tutorial that I recorded some time ago in my functional programming series, where I explained in great detail how to do that. So what is fully parametric code? Intuitively, it's code that works in the same way for all type parameters. What does it mean? Now it's an example of a fully parametric function. Imagine we have a list which we define like this. Well, just for convenience, it's a short definition of list. And then we define oh, okay, so this is actually inconsistent. Very sorry. I'm using a standard list class in this code. I will delete this from the slides after the recording. So let's ignore this. And this is the standard Scala list. So we implement the head option function. It's a function with this type signature, and this is the code. Now if you look at this code, it does not look at any type. It says whatever type A is, the code is the same. The code is written completely the same way for all types. This you can see as an example of a fully parametric type definition. Now, as I said, this is not the list constructor that I'm using in this code. I will have to delete this from the slide, but you see this type does not use any specific types other than the given type parameters. So it has a type expression which is built up from some other types, but only from the type parameter A. There is option is a standard type which can be defined. List is being defined here. So this is an example of a fully parametric definition of a type. Here's an example of code that is not fully parametric. It will be a definition of head option that would check whether the type is integer, and if it's integer, then we add 100 to that value. Otherwise, we return the first element of the list. Now this code is still purely functional. It's referentially transparent. It gives you always the same result for the same input. It does not have any side effects, but it is not fully parametric. And this code violates the naturality law. So if you first apply a map with some function and then head option, or first head option and then a map, you get different results because you're adding 100. So the problem is that we are using this specific type detection, which is not allowed in fully parametric code. Now, what is allowed? All argument types must be combinations of type parameters, and all type parameters must be treated as unknown and arbitrary types. So we're not allowed to use specific types, no values of specific types either. So cannot use value 100 or something like this. Of course, we should not be using any side effects or null or exceptions or runtime detection of types or any external libraries. So no loading of code from external libraries, none of that. So the code must be purely functional, but there's a stronger restriction that we're not allowed to do this. So we're not allowed to write code like this. This code is purely functional, but not fully parametric. If we write purely functional code, but only use unit type and values. Unit values, that's fine. So unit value is allowed. So option can be seen as a type defined using unit, and so that's fine. Either can be defined, that's fine. So algebraic data types are fine as long as they don't use specific types like integer or string. That you cannot use. And also hard-coded values of those types you cannot use. So as long as your code is like this, that's fully parametric. So code of functions like map, filter, that's always fully parametric. The Boolean type can be seen as either of unit and unit, so it's also fully parametric. And one can specify quite precisely what are the allowed elements of code that are fully parametric. And there are 9 constructions that you're allowed to use in your code. You can use unit value, you can use a bound variable, so argument of your function is a bound variable, you can use it. You can create a function, you can use a function by applying to an argument, you can create a tuple, you can use a tuple, such as _1 or _2 or some other tuple you can have. You can create a disjunctive value, something like this, either left or right. You can use a disjunctive value by writing a case expression with pattern matching. And also you can use a recursive call, so you can use the same function in its own definition. That's fine too. Here's an example of fmap for list of pairs. So it's a special case, so it's a list of pairs, list of AA to list of BB. And this code illustrates all 9 code constructions. So first of all, it's a function, so we create a function. And that's construction 3. Then we use a case expression, construction 8. Nil is a unit type with a name, so that's construction 1. We are allowed to use unit type or equivalent named unit type, so to speak. Now, here we're creating a disjunctive type, so list is a disjunctive type, so we're creating it. We're using pattern matching, that's fine. We're creating a tuple, f of this, comma, f of this. We are using a tuple by extracting values from a tuple. And then we are using the function recursively, calling the same function in its own definition. So we have used all 9 constructions in this example. So now you know what it is that you have to write. So as long as you write fully parametric code, this code will satisfy the naturality law. Now, the parametricity theorem, as explained in these papers, is not easy to understand and to use. So this paper is what I already showed. This paper is a previous paper that explained the theory behind it in a different way. But they're using an approach that is hard to use. It's an approach of relations. Now, relations means first you need to replace functions, which are one-to-one or many-to-one, by relations that are many-to-many. Then you have to derive a law using relation variables. Now, what are relation variables? It's hard to explain, and you have to learn what that is. Then after that, you replace those relations by functions so that you can write down an equation that you can use in your code. Because in your code, you don't have any relation variables. You have ordinary function in your code. So not only you have to learn first how to work with relations, and not only relation values, but also relation types. It's kind of a theory that you have to learn. But then you have to discard all those relations because you have to replace them by functions. And only then you get a law in the form of an equation that you can use in your code. There's an alternative approach, the one that I like a bit better, which is based on the so-called dinatural transformations. And that approach was developed in some other papers that are much less known. This approach gives you naturality laws directly. There's no need to use relations. You start from a type signature containing arbitrary type constructors, and you quickly write down the naturality law, or dinaturality law. Whereas in these papers, you don't see that. You don't see how to quickly do that. It's a roundabout procedure that's hard to follow. So what are those dinaturality laws and dinatural transformations? Those are, as I said, more general forms of natural transformations. And the more general form is necessary because not all functions have type signatures of this form, where f and g are both functors or both contrafunctors. Sometimes transformations do not have this type signature. Here's an example. This transformation does not have this type signature, this form. It's a different type signature where the type parameter a, here it is covariant, here it is contravariant, here it is covariant. And so another example is fold, which has two type parameters. And type parameter a is fine. You can imagine that this is covariant and this is covariant in A. But parameter B is not like that. So here's contravariant, here's covariant, here's contravariant, here's covariant. So parameter B cannot be seen to have a type signature of this form. It's at once in covariant and contravariant positions, which gives us neither a functor nor a contrafunctor. Nevertheless, because the code is fully parametric, its type must be such that we can identify where the parameter is covariant and where it is contravariant. And so we can separate these two usages into two different type parameters temporarily using something called a profunctor, which is a type constructor with two type parameters, contravariant in the first type parameter and covariant in the second. It's like a function from x to y, which will be contravariant in x and covariant in y. And then, once we label, for example, here b is contravariant, here b is covariant, contravariant, and we just replace the covariant ones with y and contravariant ones with x, at the end, we will set them to be equal. And so then we will recover this type signature. That's the trick. So we separate covariant and contravariant usages, and then each function will be written in this form then, where p and q are some profunctors. Because you can always say, okay, well, let's take this, for example. We have here list of A, and this is the big type constructor. So let's say list of A doesn't depend on B at all, so this will be a constant profunctor, and this will be a profunctor containing A as a other type parameter, and B, instead of B, we'll use X and Y. So here it will be contravariant, so it will be X, covariant will be Y, contravariant X, covariant Y. And so then we will replace at the end both X and Y with B and B. And in this way, it is clear that any type signature can be written somehow in this form, where P and Q are some type constructors, contravariant in one and covariant in the other parameter. And so this is a dinatural transformation that has this type signature, and all pure functions, all purely fully parametric functions, have the type signature of dinatural transformation. Now, what is the law that they have to satisfy? This law is complicated, and it's illustrated in this type diagram. the law is formulated for all functions f of type a to b. And I'm using this pipe function, which is defined in Scala 2.13, very convenient thing, which applies a function to an argument where the argument is to the left of the function. So x.pipe of f is f of x. So this law is applied to arbitrary values of type p of ba. Now this is important. It's not a law that's applying to a value of type PAA. We start with a value of type BA, PBA, then we apply the contramap with respect to the type parameter B, and we get P of AA. Now then we apply this transformation T, we get Q of AA. Then we apply the map with respect to type parameter Y. So that maps A to B. Or we can first map with respect to type parameter Y, which is here A. We get P of BB. Then we apply T of B. We get Q of BB. And then we contramap with respect to type parameter X, which is this one, the first one. And we get Q of AB. And so this law says that the upper way in the diagram, which is the function P of BA to Q of AB, equals the lower path in the diagram. So this is how you would write it in Scala code. So it's quite a complicated law, but this is the most general law, which all functions will satisfy. And so this law can be reduced to natural transformation laws if P and Q are both covariant or both contravariant. In other words, when P of xy, for example, doesn't depend on x, Q of xy doesn't depend on x, then it's just P of y and Q of y, both covariant, and that's going to be simplified into a naturality law for covariant functors. Or if P of xy and Q of xy do not depend on y, then they're both contravariant, and that's going to be simplified into naturality law for contravariant functors. And so in this way, this one complicated law contains all other naturality laws as special cases. Here's an example how you would derive the naturality law for filter in this way. Now as I said, all fully parametric type signatures always have the form of a dinatural transformation with some kind of profunctors P and Q. So the first step is to derive what are the necessary profunctors P and Q given a type signature. So let's start with this type signature. So this type signature should have this form. So let's see here, P is this, and A is contravariant. So then instead of A, we write X. Q is this, and here A is contravariant, here A is covariant, so we write X and Y instead of that. So now that is the Q. So we have written the type signature of filter. It should be filter here, not filt. We write down the type signature of filter in this form. And so now we need to write down the dinaturality law, which is this big law. But we substitute specific code for map and contramap. Now what is that code? So we need to derive what is that code. The contramap for P with respect to X. What is that? Well, it's just a function, so we prepend that function to P. Map of P with respect to Y is identity because Y is not present in the type of P. So contramap of Q with respect to X is a map of F and then prepending it to this function. Map of Q with respect to Y is function Q which is this function, and then mapping with respect to f. Now I'm not deriving why that is true. That a programmer needs to learn how to write map and contramap methods for arbitrary type constructors. And that's a topic of a different tutorial. So now we can write down the Dinaturality law, which is going to be that, and we simplify and rewrite it in terms of filter rather than piping through the filter. And the result will be this. So that is a naturality law of filter derived from a very general dinaturality law, more or less mechanically. So all this is mechanically done using an algorithm. This is a law that is already written in the general form here, and we just simplify symbolically using this code. So that is the main usefulness of parametricity, but there are also other useful properties. I'll talk about two of those properties. The first one is that for bifunctors, the map calls commute when used with different type parameters. A bifunctor is a type constructor with two type parameters, which is covariant with respect to both of these type parameters. So it's covariant with respect to x, so it has a map function with respect to x, let's call it map x, and also has a different map function with respect to the type parameter y. So that's what a bifunctor is. And the commutativity law says that you can map with respect to the first type parameter, and then you can map with respect to the second type parameter. So let's say you have two functions, x to p, y to q, and so you can first map x to p and then y to q, or you first map y to q and then x to p, and the result is going to be the same value of type b of pq. So starting from any b of type b of xy, you go through this or you go through that, and the result is going to be the same value of type b of pq. So that's the commutativity law for bifunctors. And parametricity means this bifunctor is defined as a fully parametric type constructor. So it's a type constructor that only uses type parameters x and y and does not try to detect what they are and so on. And then the code for map x and map y also must be fully parametric. But it turns out that you always can write down fully parametric code like this. This is all fully parametric code, never uses specific types. And so for any fully parametric bifunctor, you can write down fully parametric map functions, and then the commutativity law will hold automatically. Does not need to be verified, as long as all code is fully parametric. An example of such a bifunctor, for example, from the Zio library, we have the IO, like a type constructor with E and A. So E is the error type and A is the result type. It has two different map functions that map with respect to these two type parameters, and you would expect it to satisfy the commutativity law. Now certainly in the Zio library, the IO bifunctor is not implemented using fully parametric code. It's a very complicated data type. It has low-level threads in it, perhaps, and so on, support for multitasking, parallel and concurrent computation. But you would still expect it to satisfy the commutativity law, and for the Zio library, you would have to verify by hand that the law holds. But if that were a type constructor defined using fully parametric code, you would not have to verify the commutativity law by hand. The second example of using parametricity is a theorem that if you have a functor, that then the map method can be written satisfying the laws of map in a fully parametric code, and that's a unique implementation. So there's a unique fully parametric lawful implementation of map. In other words, a type constructor that is fully parametric and is covariant in a type parameter admits a unique map method that is lawful and fully parametric. So that can be proved. I'm not showing you the proofs of these two statements in this tutorial, but in the interest of time, but they are proven. And it's interesting that functors have a unique implementation of map because many other type classes do not have unique implementations. A monoid does not have unique implementations. Filterable, monad, applicative, they do not have unique implementations. For this, even for the same type constructor, you can have different inequivalent implementations of the same type class. So, for example, the monad, you can have different implementations for certain type classes. For some you cannot, but for certain, for example, the writer monad depends on the monoid for the writer type, but the monoids are not unique. You could have, for example, integers. You can have different monoids, monoids with addition and monoid with multiplication, for example. So those instances are not unique. Many type classes have non-unique instances, but the functor as well as contrafunctor type classes, they have unique type instances. So the same results hold also for contrafunctors and profunctors, so not only for functors. So these are properties that are useful in practice. So it's useful to know that you can map two different type parameters in any order. So by programmers' convenience, you can choose one or another order. The results are guaranteed to be the same. And it's useful to know that the map method is unique. So essentially, you could have a library that automatically implements the map method for your data types. And it's guaranteed to produce correct code. You don't have to look at that code. Or don't have to test that code, and so on. In summary, as long as you have fully parametric code, you have enabled certain kinds of rigorous, powerful reasoning about that code. And these are specific results that come from this reasoning. Naturality laws that you can write down, and they're guaranteed to hold, so you know that your refactorings are correct. You don't need to test those refactorings. You can reduce the number of type parameters in certain type classes, and you know that it's guaranteed to be equivalent. Naturality laws are going to be holding automatically in your type class instances. You don't have to test them or prove that they hold. You know that type classes for functor, contrafunctor, and profunctor have unique instances for fully parametric type constructors. And so you don't have to write them yourself. You could write a library that would generate that code for you. That would be guaranteed correct. Bifunctors and profunctors, or generally type constructors with more than one type parameter, always obey the commutativity law. You can map or contramap with respect to different type parameters in any order, and the result is going to be the same. So these are specific and practically useful applications of parametricity theory, which are enabled as long as you have fully parametric code. So actually it is theorems not for free. The fully parametric code is a specific restriction that you are only allowed to use these 9 constructions, and once you accept that restriction, that's the price you pay for the supposedly free theorems. So they're not free, really, but this price is acceptable in many cases, and once you do that, you have all these benefits. In my book that I'm writing, I have full details and proofs of all these statements in Appendix D. So if you're interested in more details, take a look at the draft of this book where all of this is explained in great detail. This concludes the tutorial.